Hello everyone. Today I would like to go through a brief introduction of the LLVM intermediate representation, the IR for short. This will be a introduction to reading the IR primarily. I will make a second video discussing how to actually create the IR, in particular from the C++ API. But first we need to read, say, what Clang does and its middle stage to understand what it's translating from, say, C or C++ into a form which then we can generate for equivalent syntax in our language. So, firstly, LLVM IR is so the first thing to understand with firstly we will try reading some LLVM IR, but there is a nice long web page discussing the full language in a lot more depth than I will be going into, but I'm just going to give enough of the basics to understand what is happening. So in LLVMIR, if we ignore the debugging instrumentation here, we'll notice that what we have is a function which returns some I32, and it's defined, and it takes in two parameters. In Clang's case here, it doesn't specify a name, and so the IR decides to use %0 and %1. However, if you do specify a name, it'll become % your variable name. So you'll notice that our function 1 here, which multiplies two numbers and then divides them by 2, is written like this in LLVMIR. We multiply the parameters together, followed by a division by 2. And you notice the 2 here it does not start with a %, meaning that is a literal. So this gets into the SSA form. You'll notice that all of the variables are assigned to once. The variable 0 and 1 are bound only at the call site, and then the variables 3 and 4 are only bound by these equal signs. You'll later see, in cases, say, like the factorial function down here with looping, that this IR does not try to assign to a variable more than once, even though a variable may not be assigned to in a given control flow, which we'll see in our next example. This is called the static single assignment form. This is useful for optimizations, as we can rename a variable at every point in its chain without worrying about whether we're reassigning or changing something else to rather complex. So for our next function, we will see how LLVM handles a short-circuiting operation, that being the OR in C and C++, and also how it handles multiple returns. So you'll notice that the first thing it does is it calls to the function f. And if the function f is true, it branches to label 6, otherwise it branches to label 4. So when it goes to label 6, which is the true case, it will then add 1 to the first parameter, and then branch to label 8. Notice how this is our x. So this line here implements the x plus 1 operation. The other case, the for block, the for branch, goes and calls g, and then branches based on whether g is true. If it is true, it goes also to label 6, otherwise it goes to label 8. So you'll notice here that in these blocks, there is only ever one exit. It's not like assembly, say, where there are multiple possible exits from one block of assembly. There is only ever one exit. This is the concept of the basic block. You'll see this later in the factorial example better, but in a basic block, there is only one entry point at the start, and it may come from multiple places, but there's only ever one, and there's only one exit point at the end, and it may exit to multiple different places, as the branch instruction suggests, but only ever exits from one location. This allows, again, for more optimization. Finally, we'll see at label 8, which both of these converge to. We have a PHY node. What the PHY node does is it says that its value is always going to be based on where we came from. That is, what was the last block we evaluated. So, in this case, we have, if you came from block 6, we would select value 7, which was assigned in that block. Otherwise, we would select, otherwise if you came from block 4, from here, we would select, from here specifically, we select item 1. You'll notice that even though item 7 may not be assigned if you come from block 4, as it is as item 7 is assigned in block 6, it never will be read in that case, because the PHY node will only evaluate the value at 4. A note about PHY nodes is that they tend to be at the top of blocks. In fact, they are required to be the first set of instructions in a block if they're needed. So when you have PHY nodes, they are taking their data, they are always processing data based on the control flow. You can imagine LLVM IR as a machine with infinite registers. And what a PHY node does is it says, I will select which of these two registers based on our last program counter value. Now, this is not how actual machines work, so the PHY node will eventually be resolved into, say, a common register or a conditional move of some sort. And finally, we have an actual function to look at, the factorial function. So you'll notice here that this SLT is a signed less than. The importance here is that LLVM does not distinguish values based on whether they are doesn't really distinguish values on whether they are signed and unsigned in the type name. So for example, if I change this to an unsigned number, you'll notice that down here, this variable did not change type. It's still an I32. However, here, you'll notice that the instruction changed. Now instead of being a set less than, it's an equality check, because the compiler is seeing that, well, the only case that this is ever true, that this will ever be false initially, is if this x is 0. So, and let's also make this value unsigned just to show that it will still produce it will do something similar. So you'll notice that we have here, we check whether it's 0. If it is 0, we branch to label 3, which in this case would only use the value 1, because we come from the block 1, and then we would return that 1, because the result would be 1. However, if we go to label 5, we'll notice that label 5 has two PHY nodes, because it's resolving two different values. Both will be set to 1 initially, but then we will create value 8, which is multiplying the two values that we resolved, 7 and 6. We then make value 9, which is just the value 6 plus 1. And then we compare unsigned greater than between the parameter 0 and the value of 9. If that is true, we branch the return. Basically, if whatever's in 9 is now greater than our input parameter, we leave. Otherwise, we go back to label 5. Now you'll notice that values 6 and 7 will now have the values from 8 and 9. So even though we're in a static single assignment form, the PHY node allows us to update values by passing them through multiple different labels. So, for example, the value of 9 here seems to be acting for I. So, I is initially set to 1. That's stored into 6. Then we do I times the result. Then we add 1 to I, and then we check if I is great, and then we check that I is still less than or equal to our input. And you'll notice that because 9 and 6 collectively share the responsibility of holding the value of I, that chain is updating I. It's just updating it by reassigning it to different values. Now, you'll also notice that there are certain attributes for these functions. So for example here, LLVM is saying things like, oh, function 3 here, this function 0 here, wherever this 0 is, which is, if I believe correctly, this 0, means that this function is no free, so it doesn't free any memory, it doesn't recurse either, and it doesn't have unwinding data, so that means it doesn't have exceptions. So these attributes are useful for the compiler in further optimizations, but generally, unless you need some great benefit from your compiled assembly, they're not that useful. Next time, I will be talking about how to actually generate this IR using the C++ API. Thank you.